Hi guys, in this video we're going to take a look at the properties of the binomial distribution. In the last video we learnt that a binomial experiment consists of n identical Bernoulli trials with probability of success p and probability of failure q. Now we know from looking at individual Bernoulli trials that for any discrete variable x, the expected value or mu is equal to the probability of success p. We also know that sigma squared, or the variance of x, is equal to p times q, or p times 1 minus p if you want to use just a single variable. And therefore sigma, which is the square root of the variance, also known as the standard deviation, is the square root of p times q. This makes it really easy to work out the same values for a binomial distribution, as the binomial distribution is just n Bernoulli trials done in a row. This means the expected value is just n times p. The variance is n times p times q, and the standard deviation is the square root of npq. What we'll do now is take a look at binomial distributions, and we'll remember that a distribution considers every possible value in the discrete random variable. The first case we're going to look at occurs when p, or the probability of success, is 0.5. This corresponds to examples including things like flipping coins. So in this example we might have flipped our coin 10 times and we're looking at the number of heads. Now because heads and tails are equally likely in this case, the expected value, n times p, 10 times half, equals 5. We expect to get 5 heads and 5 tails. So the center of this distribution is at the center of the range of possible values. And in fact, it's completely symmetric because getting 4 heads is just as likely as getting 4 tails. So 4 tails is 6 heads. So 4 heads and 6 heads are equal. 3 heads and 7 heads are equal, because getting 7 heads is equivalent to getting 3 tails. And since both are equally as likely, they're actually the same consideration. We could have actually defined in the first place our tails as being successful, and we'd get exactly the same graph. So it's easy to see that it has to be symmetric. As we change p though, that symmetry is lost, which we'll see now. Now we take a look at 2 other graphs that show what would happen when p equals 0.25 or 0.9. In the 0.25 case, we have an expected value of 0.25 times 10 is 2.5. So our most common value is going to be somewhere down that end of the range. In the 0.9 case, we would expect to see 9 out of 10 of the trials be successful. So the expected value is going to be 9, and the most common values will be around those high numbers there. What happens, of course, is that around our most common value, we've got more or less above or below, and so we can't spread our probability symmetrically anymore. What ends up happening is it becomes skewed to one side. In the case of p equals 0.25, we get positive skew because the tail is extended on the positive side of the distribution. And for the p equals 0.9 case, we have an example of negative skew. Only in the case of p equals 0.5 will we end up with a symmetric distribution.